So the next video in our higher vector series is on the scalar product, also known as the dot product. And the scalar product of two vectors is given by this formula that's on our formula sheet at higher mass, and it's a dot b equals the magnitude of a times the magnitude of b times cos of theta, where theta is the angle between a and b, or whichever vectors it is you've been given. So the scalar product of two vectors, a and b, is a form of vector multiplication. The answer or the result of a dot b is a number, not a vector, and that's the reason it's called the scalar product. Now, if you look at the two diagrams about 2/3 of the way down the page, you can see that when we're working out the scalar product, it matters what direction the vectors are coming out from the vertex of the angle between them. And they either have to both be pointing away from that vertex, like it is in the first diagram, or both pointing into that vertex, like you can see in the second diagram. If for some reason one vector is pointing away from the angle while the other one points into the angle, then the formula is going to change to a dot b equals negative the magnitude of a times the magnitude of b times cos theta. This variation on the scalar product is not on the formula sheet, but it is something that you need to be aware of, particularly when we come to expanding brackets. So if we look at this first example, we're going to evaluate a dot b. We've got vector A coming out from a vertex at 60 degrees to vector B that's coming out in the same vertex, and you can see that the arrows on those vertices are pointing both out from that vertex, so we can use the formula straight off of the formula sheet. So the first thing you're going to do is go to your formula sheet and you're going to write down a dot b equals the magnitude of A multiplied by the magnitude of B times cos of the angle in between them. Now if we go back to the diagram, you can see that the magnitude of A, which is the size of A, is 7, and the magnitude of B, which is the length of B, is 10. So we're going to substitute those values in. So we're saying that a dot b equals 7 multiplied by 10 multiplied by 60. Now, if you put cos 60 into your calculator, making sure that it's in degrees mode and not radians mode, you'll find that cos of 60 equals a half. And later on in the course, when we start doing exact values, that may be something that you would need to know for a non-calculator paper question. 7 times 10 is 70, multiplied by a half gives us 35, which gives us our numerical value for a dot b. So for this particular diagram, our scalar product equals 35. Now there are two special cases when it comes to scalar product. One is when the angle is 0 degrees, and the other is when the angle is 90 degrees. So if we draw ourselves a sketch of what an angle of 0 degrees might look like, if we make our vertex and we draw our vector, let's call it A, coming out from that vertex, if we don't have any angle, then basically our scalar product is going to end up being A dot A, because if there's no angle there, then vector A is just going to lie on top of itself. So from our scalar product, we know that it's the magnitude of the first vector multiplied by the magnitude of the second vector, which in this case is A again, and cos 0. Now, going back to our nat5 trig curves, we know that our cosine curve looks something a bit like that, where cos 0 equals 1, because our maximum and minimum values are 1 and -1 of a traditional cosine curve. So if we substitute that in, we have the magnitude of A multiplied by the magnitude of A again, multiplied by cos multiplied by 1. Substitute that value in. And so we can simplify that down to being the magnitude of A all squared. Now, let's have a think about a 90-degree angle. So this time we've got vector A coming out from our vertex, and we're going to make sure that vector B is going at 90 degrees. And remember, both of our arrows have to be going out of or into that vertex. So this time we're going to have A dot B. And this time we're going to have the magnitude of A multiplied by the magnitude of B multiplied by cos of 90. Now, if we go back up to our curve above and see at 90 degrees, cos of 90 is going to equal 0. So if we substitute those values in, we've got the magnitude of A multiplied by the magnitude of B multiplied by 0. And we know that anything multiplied by 0 is going to be 0. And this is a particularly special case because we can prove that anything is perpendicular if the scalar product is 0, but we can show that the converse of the statement is true. And so if we have the scalar product of two vectors is 0, then the two vectors are perpendicular. And we'll be looking at that in more detail later. So there are two other results that we need to be aware of when it comes to the scalar product. The scalar product is something called commutative. And if you think back to adding and multiplying any numbers or algebraic terms, you can do adding and multiplying in any order, and that's what commutative means. So A dot B is going to have the same value as B dot A. Also, the scalar product is distributive over vector addition. And that's just a fancy way of saying that if we expand our brackets, we can use the scalar product to find out a particular scalar value. So you can see here we've got A dot B plus C in a bracket equals A dot B plus A dot C. So to work out this scalar product, we would work out the scalar product of A dot B, and we'd work out the scalar product of A dot C, and then we would add them together. You cannot just add the vectors B and C together and then work out the scalar product, because remember, the scalar product, well, the one that we're looking at the moment, is working with magnitudes. So we've been given. So in this diagram, A, B, and C are vectors of each side of a right-angled triangle. Now let's annotate this diagram. We're being told that A has a magnitude of 5 and B has a magnitude of 4. Now we want to know what the magnitude of C is, and we can do 5 squared, take away 4 squared and square root it, or we can recognize that it's a 3, 4, 5 triangle, and so the magnitude of C is going to be 3. We're also given some information about the angles. We're told it's a right angle triangle, and we're told that this angle between vectors A and B is 30 degrees. And using our properties of a triangle, we can then work out that the angle up here between A and C is therefore going to be 60 degrees. So we've been asked to calculate A dot B minus C. So the first thing we're going to do is we're going to expand that bracket. So if we've got A dot B minus C, we know that we're going to have to work out A dot B, and we're going to then take away A dot C. So let's work out both of those parts separately. So A dot B is going to be the magnitude of A multiplied by the magnitude of B multiplied by cos of the angle in between them. So the magnitude of A is 5, the magnitude of B is 4, and we're multiplying that by cos of 30. And again, this is another of our exact values. So your calculator will show you that it's 5 times 4 times root 3 over 2. And that gives us an A dot B value of 10 root 3. Then we're going to work out A dot C. So A dot C is going to be the magnitude of A times the magnitude of C times cos of the angle in between. Now we just want to double check the direction of our arrows, and you can see this time they're both pointing into the vertex, so we don't have to make this negative. So the magnitude of A is 5. We've calculated that the magnitude of C is 3, and the angle in between this time is cos 60. So we're going to do 5 times 3 times, and we know from a previous slide, and also our calculator will tell us, as long as it's in degrees mode, that cos of 60 is a half. And we're going to leave this as a fraction, 15 over 2. So then all we have to do now is substitute it into our A dot B minus C. And we're saying that 10 root 3 minus 15 over 2 is our scalar product for this particular example. And we can't simplify it any further because we don't have any surds. For the 15 over 2, it's just a constant term. So our final answer is A dot B minus C equals 10 root 3 minus 15 over 2.